When we started to do the attributes of the different shapes, you realized that triangles stood alone. That was the easiest and had the fewest number of sides. A square could be divided into 2 triangles. A pentagon we could divide into 3 internal triangles, and it just got more and more as we progressed through octagons and dodecagons. Everything kept coming back to that idea that there were triangles within the shapes that had lots and lots of sides to them. So triangles must be an important part to geometry. In fact, Pythagorean and the trigonomic functions, those also dealt with figuring out the degree angles in a triangle and the measure of the sides of a triangle. Pythagorean a squared plus b squared equals c squared gave us information about a triangle's sides. Trigonomic functions of sine, cosine, and tangent allowed us to be able to figure out the measure of the angles, and also we could figure out the sides. But these two types of formulas, the two categories, were not horrible to work with, but it did take a little effort in order to do square roots and then all the looking up on the charts, or else going back into our computers to get the equivalent. There were a lot of pieces, moving parts to that one. So when we can have a shortcut with some of these, wouldn't that be nice? And there are 2 kinds of right triangles that actually afford a shortcut. And I want to be sure to let you in on that. When you actually get involved with geometry and then finding congruent triangles and equivalent sides and some of the more mathy parts of it, you will need all the basic things that we've talked about so far in the vocabulary and also in understanding the attributes of these shapes. The right triangle that is a 30, 60, 90 triangle is really made from a rectangle. Here I've got a rectangle that I could divide into 2 separate pieces, 2 separate triangles on this if the diagonal is cut from one vertex to another. It could also be cut in this direction. I just chose that one for my illustration. This is a scalene triangle, and we've got 3 sides of it that have different measures. But because it's a 30, 60, 90 triangle, we already know the angle measures. So figuring out the lengths of the sides can be done with these special ratios. The sides have a special ratio between them. The smallest angle in a triangle, if you go directly across from the smallest angle, you will find the smallest side measure to the triangle. The second largest gives you the second largest size, length, and the 90-degree angle always gives you the hypotenuse in the right triangle, and that would be the largest number going. So this particular ratio of knowing your x value, doubling it for the longest side, and then having this x square root 3, this always is in this ratio for a 30, 60, 90 triangle. The ratios change a little bit when we get into a right isosceles triangle. This scalene triangle was built on a rectangle. Half of a rectangle gave us that. Half of a square gives us the 45, 45, 90 triangle. And the ratios between the sides on this would be x and x, because this would be the same number since across from this 45-degree angle is, if we call this x, then across from the second 45-degree angle would also be the same length of this side. So we're going to use x twice on this. The hypotenuse, which is directly across from the 90-degree angle, has this ratio of x radical 2. Now that may not mean a whole lot to you, except you'll want to put this into your notes. The triangles, draw yourself the triangle and give yourself the ratios so you can refer to these, and we'll do some examples.